All right, so let's try to understand this representation of images, which is used by computers. So we call this digital image, and it's kind of sampling of like a continuous signal which is present in like 3D world. For example, if this is an image, so of course this image is like taken from like a real 3D world and 3D environment, right? So we have like everything. We have clouds, we have this greenery, then we have this person's arm over here. So the way we represent this image, which is called like digital images, we have this array, all right? And in this array, we have, let's say, x-axis and y-axis. So we'll have like certain number of columns, certain number of rows. And at each location, we'll have some value. So each image is represented in form of this array. And the value in this location actually represents what is being shown corresponding to that location in this image. All right, so let's try to understand this in more detail. So first of all, there are like two types of images, grayscale and colored images. We'll talk about colored images later. Let's first try to understand how grayscale images are represented. So what we do is we have that array, and each value or each pixel in that array is a number, and that number is between this range. It goes from 0 to this number. All right, I will explain what this is. Now, the A superscript over here, it's like bit level. All right, so for example, if your bit level is 16, so it will be like 2 raised to power 16, then -1. So that will be the maximum number you can have in your image. All right. Now, if you have like a higher bit level, which means that you can have a higher range of values in your image, which means that your image will be more detailed. But if A is very small, then you won't have like a lot of possible values which your image can take. So higher bit level means very finely like a defined image. But if a bit level is low, it means like it's kind of a coarse level. Right. So usually what we have is all the images which we capture these days using our phones, camera phones, it has a bit level of 8, which means that the range of this number will go from 0 to 255. Right? And in this case, 0 represents like completely black, which means nothing is present there. It's like a black color. And 255 represents white. So everything in between is kind of mix of black and white. So it's all right. So that's like one extreme. And this is like a very standard way to store images. Of course, we have like higher bits as well, because for some application, we need more details. But this is the most important one. The second is, let's say if A is equals to 1. So this is called like a 1-bit image. So if we use A equals to 1 in this particular equation, then you can say that the only possible values will be 0 and 1. Right? Which means that the pixels in that image, they will be either 0 or they will be 1. So it's kind of a binary image because you only have 2 values. So if you have a bit level of 1, that's called binary image. And if you have like a bit level which is more than 1, it's kind of grayscale image, because then you will have more details about each pixel. All right, so here are some samples, like it's the same image, but just different bit levels. On the rightmost side, you can see that the bit level is 2. So you will have like 4 different colors. If you put like 2 in this equation, we'll get like 0, 1, 2, 3. And this is a bit level of 3, and this is bit level of 8. So one thing you can observe is that when we have a bit level of 8, these will be like possible colors, and it's kind of more detailed as compared to the other 2. All right, so then the question is like, why we need these like different bit levels if higher bit level is better? And of course, we always want higher bit level, but that comes with memory consumption, right? If you need bit level of 8, that requires a lot more memory as compared to bit level of 2. So that was all about grayscale images. Now let's try to understand how the colored images are formed. And it's actually pretty simple. If you have understood like how grayscale images are formed, RGB is like a straightforward extension. And in this case, what we have is we have 3 different channels for each band. All right, so this is a RGB image, but exactly this is not like just one channel. We have 3 different channels for this. All right, so RGB, R stands for red, and this is green, and this is blue. And each of these images actually represented exactly the same way I described the grayscale image. All right, the only difference is in that case, it was going from 0 to 255, representing white and all the way up to black. In this case, it's saying that, okay, no red, all the way up to like complete full red. All right, and this is for green, and this is for blue. So RGB image is nothing but 3 different channels. And when you combine these 3 together, this RGB image is formed. Okay, so let's try to understand a little more detail, like how these RGB channels work for us as humans. And we do have these cone cells, right? And these cone cells are like corresponding to either red, green, or blue. I will talk a little more about this in the next slide. So one thing to understand is light has a wavelength, and yeah, so this is an interesting fact. Like some people have 4 cone types, which means they can see like more colors. Some only have 2, which means they can see like fewer colors. So this is an interesting fact. So that's fine. So this color vision, it's a biological thing, right? It has been evolving like over so many years, million of years, in fact. And if you look at like the complete the wavelength band of light, the human vision like to which we respond is between 400 to 700 nanometer. Okay, so this is the wavelength where we see colors. This is like to which our human system actually responds. And all the way on this right, the 700, this is like corresponding to red. So that's what this plot is showing you. And it peaks at this location around like, I would say 560 or 570. And on the left, then we have this green. And then on the left, we have this blue. So this is like the patch of the wavelength band to which human vision responds. And that's how it's distributed. So there are like cones inside our fovea, which are actually responsible for this. And of course, man, if there's no light, there won't be any color. So light is making all this possible. And regarding grayscale, like we can only discriminate between bunch of grayscale values, but when it comes to colors, we can discriminate between thousands of different colors. And all that is like a credit to the cones we have in our fovea. Okay, so these cones are actually located right over here. And when light falls there, so depending upon like what wavelength it is, the cones respond. And of course, like we'll have different cones for different colors. For example, for red, we have almost like 64%, green 32%, and blue only about 2% of cones. Right. And the other important these perceivers, neo-perceivers we have, it's called rods. So as these cones are responsible for colors, these rods are like, they're important, and they allow us to like see like in a very dim light. And these are much more than like the amount of cones we have. This is roughly 120 millions. And these only like it's just as a grayscale image, like it will just say that whether something is present or not, and it won't discriminate between different colors. And as I said, like some humans only have 2 cones. And another interesting fact is like dogs also have just 2 types of cones. So those guys who have only 2 cones, their vision is like, we can say, same as like dogs. And the important part here is if you only have 2 cones, it means that you are only able to see like those colors, right, for which you have cones present. So for example, like if you just have red and blue, you will only watch those 2 colors. You will never watch green.